Good morning, students. Today we will be discussing the various solutions to the critical section problem, which is a very well-known or popular problem being faced in operating systems. Basically, what is a critical section? A section of code. Basically, critical section is a particular section of code which is common to in cooperating processes in which some common data structures are being modified. So basically, a critical section consists of different sections of code. Among them is the entry section, then the critical section, then the exit section, then the remainder section. So I will come to these one by one. So basically, the critical section must be enforcing three very important rules, one of them is the mutual exclusion. What is that? If a particular process, say PI, is executing its critical section, then no other processes can be executing in its critical section. Now, suppose there are n number of cooperating processes. If one of the processes is been executing in its critical section, then no other particular process can be entering into its critical section. So that means mutual exclusive access is required here. Next is progress. Now, what is that? Now, if no process is executing in its critical section, and some of the processes which wish to enter into their critical section, then only those processes that are not executing in their remainder section can participate in a particular decision. For what? For allowing a particular process to enter into its critical section, and this selection cannot be postponed indefinitely. So that is all about the progress requirement. Last is bounded way. What is that? There exists a particular bound on the number of times that other processes are allowed to enter their critical sections after a particular process has made a request to enter its critical section, and before that request is granted. That means you cannot indefinitely block a particular process from entering into the critical section. So basically these three conditions must be met to solve the critical section problem. Now here a particular algorithm is being defined. Basically, it is a two. It is concerned with two processes only, two processation. And what you are doing here? So basically, the algorithm is like this. First of all, you are say a particular process, say PI, wants to enter into the critical section. So what will be the code in the critical section part? So while turn not equal to I, that means when a process PI wants to enter into the critical section, it is maintaining a particular turn variable here. So basically, in this particular algorithm, the approach which we will be taking is that the processes share a common integer variable called turn. It is initialized either to say 0 or 1 or whatever like that. So if turn equal I, then process PI will be allowed to execute in its critical section. So the structures like this, do loop is there, do while loop is there, do while turn not equal to I. That means if the turn is not equal to I, then you have to wait. Otherwise, let the process PI enter into its critical section. Uh, Let the particular process complete the critical section code. Then it will make turn equal to J. J means another process. That means now turn I equal to false. So turn is equal to now J. Then the remainder section code will be executed, and then the particular process will commence as usual. So basically, uh, this solution ensures that only one process at a time can be in its critical section, but it actually does not satisfy the progress requirement. Say one of the process, say process 1 breaks down, say at the remainder section, after making turn equal to 0, then what will happen? Process 0 will enter into its critical section, it will exit and it will make turn equal to 1, and then waits, being unable to enter into its critical section again, because process 1 has already broken down. That means progress requirement is hampered here. So basically using the common variable turn here, the particular problem is being looked into. Now another algorithm, what we have to do here. So basically, now considering the previous algorithm one, the problem with algorithm one is that it does not retain sufficient information about the state of each process. It remembers only which of the processes is allowed to enter into the critical section. Now to remedy this problem, what we can do, we can replace the variable turn with the Boolean array, say a Boolean flag. An array is called flag here, so Boolean flag having only two elements in it. So the elements of the array are initialized to false. That means if flag I is true, then that value will indicate that Pi is ready to enter into the critical section. So what is the structure of the algorithm here? Do you are starting the do while loop. Do flag I equal to true. So you're making the flag I as true here. While flag j, that means if uh, at that time flag j is true, then what you will do? You will have to wait. Otherwise, enter into the critical section. Now, after exiting the critical section, make flag I equal to false, and then go to the remainder section. So basically, here in this algorithm, the process Pi first sets flag I to be true, signaling that it is ready to enter into the critical section. Then what happens? Then PI checks. PI checks to verify that process Pj is ready or not to enter into its critical section. If Pj were ready, then Pi would wait until Pj has indicated that it no longer needed to be in the critical section. That means until flag j was false. Now at this point, Pi would enter into the critical section. On exiting the critical section, again Pi would set the flag I to be false, allowing the other process, in this case process j, to enter into its critical section. That means flag 0 keeps track of the process 0 state and flag 1 keeps track of the process 1 state. So this is another solution to handle the critical section problem. Now, the third problem, the third mechanism of the algorithm is called Peterson solution. Is a combination of both mechanisms. So basically, this particular algorithm combines the key ideas of algorithm 1 and algorithm 2, and we can obtain a correct solution to the critical section problem, where all the three requirements have been met. So basically, for this particular algorithm, the processes are sharing two variables. One is an integer variable turn, and one is the Boolean flag. So initially, flag 0 equal to flag 1 equal to false, and the value of turn is immaterial, but it is either 0 or 1. Now, what is the structure of the algorithm here? So do flag I equal to true, turn equal to j. While flag j and turn equal j do nothing, then you have to wait. Otherwise, go to the critical section, and after exiting the critical section, make flag I equal to false, and then proceed to the remainder section. So basically, here the value of the turn variable plays a very major role. How it is working here? What is the working principle? So let's see the working principle of the Peterson solution. So basically, to enter the critical section, process Pi first sets flag I to be true, and then sets turn to the value j, thereby asserting that if the other process wishes to enter into the critical section, it can do so. That means it is allowing the other process to enter into its critical section if the other process is ready. Now, if both the processes try to enter at the same time, turn will be set to both I and j at roughly the same time, but only one of these assignments will be lasting. The other will occur, but will be overwritten immediately. So any one of the processes ultimately will be allowed to enter into its critical section. So basically, the eventual value of the turn variable decides which of the two processes is being allowed to enter into its critical section first. So this particular solution satisfies all the three critical conditions for handling the critical section problem. Okay, that's all for today. We will be covering some another sections of process synchronization in the following lectures. Okay, with that we will end today's discussion. Thank you.